Hello, making a video, DraftScience. Yeah, I didn't know when to hit the button or to hit the button. I don't really have a, what do you call those lists, you know. Yeah, I don't have an itinerary for the video. So, you know, this guy, Taki Tenenga, anyway, he posted a link on one of my other videos where I was ragging about the lack of commentary on science, and anyway, he posted 3 links, and they're all videos I'd seen before, and they're all videos that don't accept comments, which just seemed kind of funny. I can't comment, so. But I think that's just kind of strange, you know, physics videos that don't take comments, and I don't know, people who have some challenge to physics and then they block you or something. I mean, it's all very strange. But anyway, so moving on. You know, strange if you're not being obscenely rude. But anyway, so one of the videos I'll play the beginning of, and you know, I've played parts of it before, I think, so you know, it might be a little bit redundant, but it just isolates the problems here. Nobody's going to respond to these problems, apparently, until I have an audience of people who feel some need to defend the physics hierarchy that's talking absolute shit. So anyway, this was an issue with Piro. Why does time slow down for clocks in motion? You know, and Piro contends that the argument is that the clocks slow down, that's what Einstein said, and that's what everybody's saying. And that's not what they're saying. Clearly in that sentence they're saying, why does time slow down for the clock in motion? They're saying that time slows down, the clock's doing just fine, it's measuring the wrong time. The time has changed, and therefore the clock is measuring a different kind of time. When in fact, no, the clock itself can't tell time accurately anymore because it's broken by the velocity. It's not an accurate time teller. The movement is breaking the clock. That's a very different argument than Einstein's argument. So, I mean, yeah. I hate to say, I mean, I'm just going to say, oh, fuck you, Piro, you're just so full of shit. You keep saying things and saying, there's your solution, there's your answer. That's not an answer. It's crap. But anyway, so we'll play this. It's only 3 minutes. I shouldn't get too lost, and we'll just see what kind of schlock this place, World Science Festival. It's some sort of non-profit. They do have these nice little get-togethers where a few scientists talk about shit, but yeah, generally speaking, they're talking shit, so what good is it? And this Greene guy is just so fucking annoying. You know, look, we got gravity in our living room. Yeah, right. You got a gravity. Look, it illustrates gravity. Exactly, it illustrates gravity. Yeah, it doesn't demonstrate. It demonstrates gravity, it doesn't illustrate gravity. There you go. Right, let's just do this. Annoying fuckers everywhere. So, Moments in Science with Brian Greene. So I guess I'll put his name in the title.
Einstein showed.
Say something derogatory.
That if you watch me as I'm walking, you will say that time elapses more slowly on my watch than it does on your watch. Time slows for an object in motion. Now that...
Time slows. So there it is again. Time slows. Your watch doesn't break, right? So, I mean, if you're moving faster, your watch isn't working as well. It slows down. Its function slows down because it has to spend time moving. So if we're relative to each other, and you're moving, and I'm not moving relative to each other, you're obviously probably going faster than me. Probably. See, this is the trick of this whole thing, is you can't do it experimentally, because there could be circumstances where there's 2 relative bodies, and you just happen to be going in the direction where both of us are both moving this way, and then you happen to go the opposite way, then I'll be the one with the broken watch, because yours will start getting better. Your watch will start improving. So it doesn't matter. There's absolutes here. This is just a pile of crap. This is synthetic math defending, bullshit drawings. Obviously, there's not a drawing here. Just some guy. Look, I'm pretending to be a teenager.
It blows your mind.
It blows your mind and confuses everyone, so I can take advantage and make lots of money selling crap.
It's so counterintuitive.
It's so full of crap because simple thought experiments illustrate paradoxical nonsense.
Never experienced that. And the reason simply is that you've never experienced speeds near the speed of light where these effects become big and obvious.
Yeah, big and obvious. No, they become even less obvious because as you're near the speed of light, you're not anything. Your clock isn't even a clock anymore. It's just a bunch of fish going that way. It's a bunch of quanta moving the speed of light in a straight line in a direction, which makes it pretty much a laser beam. So you're essentially converted your clock into a fucking laser beam, and it's not doing any time telling anymore.
So the question is, for us lowly human beings...
He's always doing this up and downy thing.
That don't travel near the speed of light. Is there a mental mnemonic, some sort of intuitive way of thinking about why...
So is there some way, intuitive way to think about it? Yes, this is it. The intuitive way to think about it is to understand that nothing moves free. There's no free motion. So if something's already moving, the little bits spinning around inside of an atom, you can't just say, oh, well, now go 1,000,000 miles an hour in that direction. They can't do that. First, they end up going faster than the speed of light, so they can't do that. So there has to be something that's happening. What's happening is their condition, their ability to do this, is changed when you obligate them to do that also. So when they have to do that plus this, it means one of these things has to be done slower. And obviously going that can't be done slower because you're obligating it to do that. So as it does that, this, it has to do slower. There. That's an intuitive way to understand it. If you're dancing, I'll do the dance. If you're dancing as fast as you can, and I say, now dance while you move right, you won't be able to dance as fast.
Is that time slows down when an object is in motion. And
right. Time doesn't slow down. The metabolism of the matter moving slows down.
And it makes use of a little metaphor that at first sight has nothing to do with time or any of these ideas.
You're just so fucking... He's hip.
Imagine that we have, say, an SUV. And that SUV...
It's got like porn music in the background. Ding, 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 ding. Oh, Chinese porn.
Is traveling at 100 kilometers per hour purely in the northward direction.
Yes, okay.
Then we imagine changing the situation slightly by having that same SUV also going 100 kilometers per hour, but now in a northeasterly direction.
Okay, so now he's going to do vector math. Cool. Okay, well that's all right with me.
And the point I want you to grasp is a simple one, which is simply this. Because part of the car's motion has now been diverted from north to east, its speed in the northward direction has slowed down, and therefore it hasn't traveled as far north as this car. And indeed, if we consider a car that's traveling even more toward the east, it's diverting even more of its original motion toward the north into eastward motion, so it travels...
This isn't even accurate, right? Because his lines are too long, so they can't be going the same speed. So if this is their starting point, quite obviously this line is a little too long. But anyway, let's, it'd be nice if they did the drawing accurately and to scale.
Even less distance in the northward direction compared to the car that's moving purely toward the north. Simple idea. Why is it relevant? Well, this notion actually has a version that applies to time. And here's how it goes. You'll see it sounds very...
Well, whatever. So, you could just say that this is the example of the dancing thing. You won't be able to do the dance this direction, so let's call that the dance. And if I force you to go another direction, you can't dance as far, or the argument would be as fast if you're going the other way. And everything else remains the same. You are physically limited to a certain speed limit, an amount of movement. And if you now change the movement you were doing as your standard movement, now you have to do some other movement. You can't add movement. You can only subtract movement from what you were doing to apply it to some new movement. So whatever new movement you have this way, you're going to have to take it from this way because your speed can't change. The internal speed.
Similar. Right now, I'm standing still, and you say I'm not moving. But if you really think in space-time terms, you realize I am moving through time. Right? My watch, if I had one, is ticking second after second after second.
Again, your watch is not time. It tells time. It reports on time. It measures time. And it can measure it accurately or it can measure it inaccurately. Period. Has nothing to do with time itself. A slow clock does not change the time around it. Time is still moving exactly the same speed.
Making me move through time. All of my motion, therefore, is purely in the time direction. Now, if I start to walk, Einstein showed that my motion through space...
He didn't show any of this shit, so that's just wrong. He didn't. The evidence is putrid.
Diverts some of my previous motion through time into that motion through space.
So again, he's just basically making the same argument that once you make time-space into a single thing, then distance is time, and we already know that. Distance is time without creating space-time. It always takes time to travel distance, and it's a standard thing, and that's why light's the constant, the speed of light. That means the speed of distance, the amount of distance you can travel in a certain amount of time. That's the speed of light. So distance has already been tied to time. You don't need to create space-time to recognize that time is the way you measure distance. A way to measure distance when your speed is relative to a constant.
And therefore my motion through time slows down, just like the motion toward the north of these cars slows down too, because that motion has been diverted into a different direction.
Well, again, that motion has been diverted into a different direction is saying absolutely nothing. I mean, it really isn't explaining how when you're standing still, your motion is being diverted now that you're moving in a direction. You have to concede that the motion you're really talking about is your atomic metabolism, because that's the only motion you have when you're standing still, technically. I mean, observable. Relative motion. Relative to your standing still, the only thing moving are your interior bits.
In this case, it's diverting a spatial motion in one direction to a spatial motion in another direction. And the interesting relative...
Yeah, well, that was not a very good explanation. You have to concede, right? You really have to concede that wasn't too good. Tying this drawing to space-time wasn't well accomplished.
In this case, it's my motion through time that's now being diverted into motion through space.
So his motion through time is being diverted into motion through space. Again, does that make any sense? Come on. Plenty of time can pass without me moving through space. So the fact that, if you're going to start turning the watch on when I move, I mean, it just doesn't make any sense. No, this doesn't make any sense. Sorry. No sale.
My motion through time slows down. And that's an intuitive way of understanding why it is that when an object is in...
Sorry, not intuitive to me at all. I'm standing still, time is ticking. I move in a direction, I've now something, and somehow my watch doesn't work. Well, that's what I'm arguing. Your watch doesn't work if you're moving, but it could be not working when you're standing still. Well, I guess the standing still was the way to just throw the whole thing in the toilet, because it's a silly notion anyway.
Motion. Time for it compared to you will elapse more slowly.
Well, there we go. Okay, compared to me. All right, so that's the thing we needed. I'm the observer. I'm sitting with you. We're both not moving relative to each other. And then somehow you start to move, and somehow that means you've bent your, warped your space-time or something. Well, it says you. I don't find that at all intuitive. So anyway, enough of that. Okay, well, that was not much fun. So moving on. Measure for measure, I think this is it. Yeah, so I'm halfway through this. I mean, I've seen it before, so, you know. They do this dart analogy. They're comparing Copenhagen to many worlds, to it's all push or something, you know, the push wave. You know, there's the Copenhagen and the push one are basically the same thing, except Copenhagen says the wave's in front of the thing, and the other one is basically saying the thing has a wave behind it, kind of. But they're all bullshit, so it doesn't really. So they, you know, they waste a lot of time on that kind of crap. I just want to get to the beginning of the video where he explains the two-slit experiment. It's just quite horrible.
Physics has really been embraced by the culture. At least the language of quantum mechanics has been embraced by the culture. I mean, just to give a couple examples, right? So from Hollywood, right? We have quantum, the family program here, right? So, don't take me to the vet. And I don't know, did any of you go to Spooky Action last year, just by any chance? Yeah, so a handful of you. So you may recall
that. Yeah, so this is 2014. I did look for the 2015 one. I didn't find one, but, you know, it's going to look harder, I suppose. Yeah. I should have looked under May, right? May 29th. So it should be somewhere around there. I'll do that later.
We actually did the double slit experiment on the stage last year. We're not going to do it again this year. We don't have enough time, but rather animations will give you the essential ideas. And if anyone doesn't believe the animations, just ask someone whose hand was up, because they saw the real experiment done last year. Okay.
Yeah, well, right, so let's just say the obvious, right? I mean, why not just show the single slit experiment? Oh, that's right, because that makes you sound like kooks.
Okay, so what is a double slit experiment? The idea is this. Imagine that I have...
All right, so let's understand that they've radically changed it. So they had this equation they're also in love with, written in 30. And clearly, back then, this isn't how the experiment was done, because it was an aperture. So they've taken away the aperture, which changes the kind of light you're going to get at the two slits. It's like using a laser beam versus the original aperture. One, you're going to get a cone of light, and one of them you're going to get colonnaded light. You're going to get light that's evenly distributed. Okay, so a laser beam is pretty much an even amount of light from edge to center, where the original two-slit experiment was done with light that was more intense in the center and less intense on the fringe. And somehow the same equation works. Now, what a surprise. Should it? No, it shouldn't.
A gun that's firing ordinary pellets, like BBs, at a barrier that has two openings. Now, you'd expect that those BBs that go through the left slit will land aligned in a band on the left. Those pellets that go through the right opening will land in a band aligned with it on the right. And indeed, we're
and the reason why they do this experiment this way, just to understand, okay, first they have a gun that can't shoot straight. That's critical. Why don't you shoot straight? See what happens. Shoot perfectly straight. See if you get what kind of pattern you get. Oh, no.
Do this experiment, that is the result that you would find. Now, what we're going to do is imagine dialing down the size of those pellets, those BBs, making them smaller and smaller until they are the size of little tiny particles. Let's just call them...
Yeah, little tiny particles that aren't particles. Electrons. Electrons aren't particles. Electrons are a mass of 1 million quanta, which is a lot of photons, essentially.
Electrons. Imagine we're doing this with electrons. Well, you'd expect that if...
And electrons don't fly straight, so it's another thing you should know. Electrons are not... they have to be. It's like they have to be a perfect sphere. It's like having a crooked frisbee. You know, lopsided weight-wise. Then you throw it, it's not going to go straight. It's going to go in the direction of its lopsidedness.
You run the same experiment. Again, those electrons that pass through the left opening will land in a band aligned with the opening on the left, and similarly for those that pass through the right. That is what you would expect should happen. And I think as many of you are familiar, this is not what happens when you do this experiment. Instead, if you do this experiment, you get results that look rather different. They look like this. You get...
Right, now you get exactly the same pattern with just one slit. So, no need for two slits. You can get exactly the same pattern. It's just that the difference between this center and this first fringe is 8 times less intense. So the fringes are less intense by a factor of 8 or 9. So they're quite a bit dimmer. But they're there. You can see them. And with laser beams, they're there clearly not by that big a difference, not a 9 times difference. So clearly it makes a difference what kind of light you shine through the single slit. If you use light that has the same intensity on the fringe as in the middle, you'll get a very strong pattern. So laser beams work really well with single slits, and they'll give you a very strong pattern. So you don't need to do 2 slits. You don't need all this controversy. You don't need all this quantum. Which slit did it go through? How do you, if you measure it, you can't tell, blah, blah. None of this is necessary. Same exact pattern, single slit. No, you don't need Copenhagen. You don't need all these waves. You don't need any waves. There's no wave diffraction. There's not 2 waves because there's 2 slits. That's the argument of the math. There's 2 waves interfering with each other, creating this pattern. Because there's 2 slits. That's what they're saying. Why are they getting away with it? Why are supposedly the icons of physics explaining reality this inaccurately?
A bright band next to a dark region, next to a bright region, next to a dark region, next to a bright region, and so forth. And that data, that strange data, is really...
is exactly what you get with 1 slit. Exactly.
What impels us toward quantum mechanics. Now that data is strange because it's not what we would think should happen. We expect to get 2 bands and we get more. But it turns out that pattern, bright, dark, is a familiar pattern to most physicists. I mean, we are trained...
Right. So, you know, he thinks it's a familiar pattern to most physicists, the standard interference pattern. Well, you can also find patterns in magnetic fields have a very strong pattern. Same exact pattern. Newton's rings, you know, lensing, very strong patterns that are created. Same exact pattern, technically, just in a circle instead of in flat bars. No different. Exactly the same phenomenon. So anyway, I think it's easy to say, oh, well, yeah, pattern in, pattern out. You could also argue that the matter itself is influencing the light as it's traveling through the pattern. The wave isn't in the photon or the electron. The wave is in the material structure. Yeah. Seems a perfectly reasonable explanation. Perfectly reasonable.
From birth to recognize that pattern, right? If you were to go to any physicist,
Yes,
3 o'clock in the morning, shake that physicist, wake them up and tell them, I got this data, bright band, dark band, bright band, dark band. The very first thing that they would say to you is, what the hell are you doing in my room at 3 o'clock in the morning?
Funny.
But after that, they would say, I know what that is. That's an interference pattern. That is the hallmark signature that there's some kind of wave phenomenon, some kind of wave phenomenon.
Right. So, I mean, it's just a deny of how we create waves, right? We create waves by creating a force. You know, you can create waves in a pond, just keep dropping drips into it. Now, the drips, when they're coming down, it's not, you don't say, hey, that's a wave of drops, right? It's not what you think. You understand them as being discrete bits. They're not waving. They're hard particle, hard particle, hard particle hitting something. You don't call them a wave. We know waves happen in mediums where there's tension, where the molecules are sticking to each other. Won't happen in mediums where, like a bunch of ball bearings or something, you can poke that all day long and you're not going to make waves.
Taking place. Right, to understand that, let me just give you a little visual here where we're looking at water waves. Imagine I throw 2 pebbles. The first one over here makes these circular ripples, and now throwing a second one, and look what happens. When the waves overlap, in some regions they work together, but in other regions the peak of one wave is crossing the trough of another, causing the wave to kick.
Right. So when this happens by just throwing one rock in, how come that didn't happen? How come if I throw one rock in a pond, this doesn't happen? There's no interference pattern. Where's the interference pattern? Where's these nice lines? Where's this stuff? None of this crap happens. Where is it? Why does it show up when I shoot photons through a single slit? Oh, that's right, because this has nothing to do with physics. This is a property of chemistry, you know, of more complex molecular bonds. This is tension. This is force moving through a tense field. This doesn't have anything to do with quantum physics. Nuclear bits.
Cancel out, and those are those dark regions that you see on the screen. So this is exactly the kind of data that we're encountering, and to make that point a little bit more...
Well, again, and to make the point again, over again, why are you describing this phenomenon as if this is something to do with 2 slits? Again, it happens with a single slit. This has nothing to do with an interference pattern. This obviously has something to do with wave, okay, mechanics being caused by when you force something through slits. If they interact with the matter they're traveling next to, the surfaces. And what's the difference between the single slit and the double slit? The double slit, the most intense light, the middle light, goes right next to the surfaces. No surprise that the diffraction pattern would be stronger because the strongest light runs right next to the surfaces. And in the single slit, the strongest light goes right through the middle, least likely to be diffracted. The furthest away it can get from a surface. The strongest light is the furthest away from the surface possible, and the 2 slit, the strongest light is the closest to an edge as possible. Are we done?
Clearly, let me just show you an animation, same idea. Imagine you've got...
Yeah, same bullshit though. Again, 2 slits. Why not do it with a single slit and just show us how the magic waves pop out of nowhere? How come we have an interference pattern when there's only one frickin' wave? Do it with 1 slit and then show me the pattern. Oh, that's right, it won't be there because it won't work. Your experiment won't work in water with a single slit. Where it will work with photons and electrons. Isn't that reason why you shouldn't be using this as an illustration? Because it's obviously doesn't have anything to do with what's going on. because it doesn't behave exactly the same, or even fundamentally the same.
Water waves going toward the barrier with the two openings, and again, regions where the waves work together, the water is very agitated. Regions in between where the peak of one wave crosses the trough of the other, they cancel each other out. And if on the back screen I put bright regions associated with very agitated water, dark regions with not agitated water, look what I...
Right, and you get the same exact pattern with a single slit, and the only difference will be this will be twice as big. And logically, you can sort of understand why it would be, because this isn't in the way. So the strongest light goes right straight through and hits the center. It's all about surfaces. It's all about moving electrons next to surfaces or photons next to surfaces. Surfaces are not, it's not like surfaces here and there's absolutely nothing on this side of it. That's not how nuclear physics works. Nuclear physics doesn't have like, here's where the atoms are and there's absolutely nothing on this side. No, nuclear physics works. There's usually stuff here, matter, condensed, and then there's a less condensed medium in between. I mean, in our case, atmosphere, but even in empty space, we know it's full of all kinds of charged particles.
Again, bright, dark, bright, dark, bright, dark. And again, just to remember, that is the data that we find in this experiment.
So again, I'm just saying, this is just last year. This is how they're explaining quantum mechanics and why it's a mystery. And they're leaving out of this fundamental description of why this is significant the fact that the very same pattern is created by a single slit. That to me seems far more fascinating, that you don't have your two waves, and yet you have exactly the same pattern except for one defect where the center piece is brighter. That's the only difference. No other difference. Put the light through a single slit, you get exactly the same pattern. The only difference is the central maxima, as described, is twice as bright, twice as big. That's it. Why is this being left out? Is this, Brian, are you going to tell me you don't know that truth? You don't know there's single slit diffraction? You didn't learn that in your physics courses? Every physics course I've seen online includes it. They make up the Huygens thing. You know, but whatever. I mean, if the Huygens thing is happening, then you just Huygens all of these slits and say, why are you talking about two slits? Because it's really the million Huygenses. Anyway.
So this suggests that there is some deep connection between these particles, these electrons, and this other idea, a completely separate idea of waves.
Right, so he's saying that's the connection, because it looks like water waves in one circumstance. It doesn't look like water waves in the other. The single slit looks nothing like water waves. The double slit looks like water waves. Therefore, we should draw the conclusion that it's really working like wave mechanics, and it's not really just particles going through a grating and being diffracted. When you create an opening, you create a lens. They call them apertures, right? You create a little tiny hole, and it does a thing called lensing. It bends the light. And why is the light bending? Well, because it's moving near the surfaces, and the surface of the little tiny aperture, the more surface area you create as a percentage of the entire area of the opening. So the smaller you make the hole, the more surface dominates, the likelihood of the photon going right next to the surface keeps increasing as you make the hole smaller and smaller, and you diffract more and more of the light. A clear connection between surfaces and diffraction. A clear, rational, logical, follow the evidence conclusion. The surface diffracts light. fuck? It's so obvious.
Now, at first sight, that might not actually seem all that surprising, right? Because water has water waves, but we all know that water is itself made of little particles, molecules, H2O molecules. So
but again, why are you comparing electrons and photons to water? There's no evidence that electrons are bound to each other at all, that there's any tension between them at all. So clearly they're not going to act like waves. They're not going to have any tension. They have exactly the opposite. They are anti-tense. They don't like each other. And there's absolutely no evidence that you know, at least electrons you can bend with magnetism and stuff, so there's some evidence of their influenceability. But photons you're not going to be able to influence at all.
certainly we know that if a large collection of molecules behaves in a choreographed manner, those particles can yield a wave. So maybe what's going on in the experiment is just that. You've got a lot of...
So now he's saying, basically, this is his metaphor, that light or electrons are flowing through here like a wave, like they're a beam wave, and it's the beam waves that are interfering with each other. That's the argument. So they completely just invented this idea of somehow the photons being connected to each other, that somehow they're tied together, that somehow their wave and frequency is completely tied together. If I move one end of the photon out, that all the other ends stretch or something. They're all tied together. They're all bound to each other. No evidence of any of that. Absolutely none.
Electrons, and maybe they are behaving in a choreographed manner, and that way yielding a...
Yeah, and we know that they're not. Clearly they can't act in a choreographed way, in a manner, because their charge doesn't allow them to. Unless you have them in a pressurized container. They can't do what you're saying they're doing.
Wave, just like H2O molecules yield a water wave. Now, how would you test that idea? Well, you can run this very
Make an
experiment.
aperture. That's right. You can run this very experiment and cover one of these holes and move this gun over and shoot it there and get the same pattern. Or you can make an aperture that you can make smaller and smaller and smaller, and you can watch it happen right before your eyes, where the light goes straight through, hits a little spot in the center when it's a big hole, and as you make the hole smaller and smaller and smaller, and you increase the likelihood that the light goes right against the edge of the material, all of a sudden you start getting all kinds of diffraction. You start getting these little halos around the dot, and halos and halos and halos, and as you make the hole smaller and smaller and smaller, you get more and more halos. Dimmer and dimmer, though. They expand. You expand the size at the same time, so that's the trick of it. So you're not going to be able to see them once you get really small, because they're going to get so dim because of the amount of diffraction. You're going to be diffracting light by feet, by huge angles. You'll have very strong amounts of diffraction as you increase the likelihood of getting closer and closer to the surface. So as you keep increasing the percentage of encounters with the surface, it depends on how close you are to the surface, right? So if I shoot something at the sun, but not at the sun, right? At the edge of the sun. Well, the closer I am to the edge, the more it's going to get bent by the gravity of the sun. And the further from the sun, the less it's going to get bent. And the same principle holds for the edge of matter. When you shoot something right next to the matter really, really close, it'll get diffracted more. And the further away it is, it gets diffracted less. That's all quite logical, correct? Matter essentially has a kind of magnetism or gravity, and then as you shoot things next to the surface of a condensed nuclear mass, photons in particular, will hit charged particles that have been trapped in those field lines. The very field lines you can see with your own eyes. Just look at a white background on your computer and you will see the little fringes right between your fingers. You'll see them happening right between your fingers. They're there. You can see diffraction. You can see that the surface is not dead. The surface is active. and the surface is what's diffracting the light. Again, just put an aperture here. Just put a hole, make the hole smaller, 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 and you'll see this pattern get wider and wider and wider. And obviously less and less intense as it gets wider because it's covering more space, quite obviously. So it's going to be more diluted. Shit.
But only firing particle by single particle at this barrier with the two openings and recording dot by single dot where each of those single particles lands on the detector screen.
Right. So there goes your whole wavy thing right out the window, right? So single particle, randomized, will be, they'll go exactly the same places they would have gone in the quick amount of time. You're just lengthening the amount of time, but all the little bits will still be going. The same number will hit here, and the same number will hit there next to a slit, and the same number will go right through the middle, and the same number will go right next to the matter. So you're having exactly the same bits. The same BBs will fly in the same positions, just slowing down when they do it. But when they do it is irrelevant. They're still going to get diffracted by the matter. They're not going to get diffracted by a magical wave function they have. They're going to get diffracted by how close they are to the matter, how close they are to the slit. How close the photon goes to the slit is going to decide where it ends up in terms of how much it's going to be diffracted. Just as how close you travel to the sun will decide how much your spaceship gets torn off of its course.
Let's run that version of the experiment and see what happens. So again, particle by single particle, we're recording on the back screen the history of all the landing locations. And
you can see it here. You know, everyone goes through this, it goes through, it's the same exact.
Dot by single dot, we build up the same pattern, the same interference pattern, the same data.
Right, so a single photon goes through a single slit and ends up at a location. So there is no interference. There's no wave that interfered. That didn't happen, quite obviously. Certainly, again, it just requires this nonsense that somehow the photon doesn't really have a photon, and that somehow it's just wave. It goes through something, and then it makes a calculation and decides where to land. But I mean, it can't be traveling on a wave. That theory goes out the window because clearly it had to go through the solid thing, had to go through one or the other slits, so that's not going to work. I mean, it can't be a solid thing, have a wave front. The wave front goes through both slits and it only goes through one. That doesn't make any sense.
That suggests to us that there must be some kind of wave-like phenomenon involved to yield.
So he says it suggests to us a wave-like phenomenon to yield. Again, why? Why does that suggest that to you? And again, if you do the same thing with a single slit, you'll get exactly the same result.
Interference pattern. So this is where things get really strange. Particles, electrons.
Yeah, this is where the whole boat of physics sinks in the mire of bullshit and never to float again. You just crash science into a fundamentally wrong conclusion. It's as bad as still thinking the earth is flat or something. You just completely broke the physics.
A little tiny dot, that is the image that we always have in mind. Waves are these spread out entities. How could a dot particle and a spread out wave somehow be connected? And this was...
Yeah, right. And so they come up with these wacky theories that the particle actually goes every possible location and there's multiverses, or they come up with some nonsense that these particles, the smallest thing in the universe, have a huge guidance system, a bunch of radar in front of them that they shoot out in front of them and do all kinds of wave calculations before they decide to land somewhere. Bullshit.
The puzzle that physicists faced in the early decades of the 20th century.
And they obviously put the puzzle together with a fucking sledgehammer. They just said, we want these pieces to add up to something fun, so let's just smash them into each other and fuck the fact that it doesn't make any goddamn sense.
And many tried to figure out what could the connection between a particle and a wave be. And the natural suggestion that you might throw out is, you know, maybe particles somehow are kind of smeared out in some way. They're kind of spread out in a way that we didn't realize. That idea, though, doesn't really work, because whenever you measure an electron, you find all of it. And if it was truly smeared out, you find a piece of it.
Yeah, well, so it's not smeared out, but it certainly has something in front of it like jelly or something, and it's the peanut butter, and yeah, it's not going to make any sense. So I'm just saying, this is physics. You know, this is what they say the truth is. This crap.
Here, and a piece of it there. And the idea that ultimately was settled upon, it came from the mind of the physicist Max Born, was that the way to think about the wave associated with a particle is this. This is the new idea.
Yes, there's a probability, and this is how it's so fucking stupid, right? So I make this aperture, right, and I make the aperture smaller and smaller. You can understand that as I'm doing that, I'm increasing the probability that the photon is going to be close to a surface. You can really understand that, right? If I have a big circle like this, what's the probability if I just randomly go in that circle somewhere that I'll be close to the surface of my finger? Right? The probability is like 50-50 or whatever, right? And it just, as I get smaller and smaller, the probability gets higher and higher. Duh. Fuck. Anyway. So this is probably enough, right?
The wave is a wave of probability. The wave is telling us the likelihood, the probability that the particle is at one location or another. So to show you a little...
Yeah, so this is the nonsense of it, right? Because now they just create an artificial description of a randomness that doesn't really exist. We know that the probability is that when you shine the light, it has an intensity, and over time, just as many particles will hit over here as hit over here. The entire area will be filled with an even distribution of particles. So this is a canard. This only, they set it up as if there's some sort of fluctuation or irregularity going in, and there isn't. But it makes their math work if they create that irregularity going in. Even though we know that it's not irregular, it's a completely even distribution of light. And what's irregular is the frequency. The light has a frequency. And the frequency of the light will decide how much it is refracted. That's like the weight of your satellite going next to the sun, or the velocity of your satellite going next to the sun. If I make your satellite heavier, it'll be more likely it's going to end up doing gravity to the sun, and it'll crash into the sun. I make it lighter, there's a better chance it's going to get through if it's going the same speed. You can sort of understand that. It changes how much it gets deflected by how massive your satellite is. Or I can just change the velocity, obviously.
Visual of that. Imagine this is the wave associated with a particle like an electron. Where the wave is big, that's a likely location to find the particle.
Well, like I said, see, this is a canard in the sense that we know that over time this turns into an entirely flat surface. The amount of time this space is down is the same amount of time it's up. The same time this is up, it's the same amount of time it's down. So we know over time this is a flat sea. So it's just a canard to say there's some mystery about where the photons are. We know they have a location, and that location will be evenly distributed. That probability is a certainty. So we might as well just establish the fact that it's quite certain where it is. There's no wave about its location. It's in a certain location, and every 1 millisecond, yes, it might be here, so this is where the peak is. But the next millisecond, it'll be here, and this is where the peak is. And over time, it'll all add up. Flip the coin enough times, and you'll have the same number of heads as tails by 99.999999999 percentage points.
The wave is small. an unlikely location. And where the wave is absolutely zero, that is a place where you simply will not find the electron at all.
Yeah, well, quite obviously we know we're not going to find it in the wall of the of the material, so it has to actually get through the slit. So yeah, but anyway, see, they're talking. You know, like I said, he's being deceptive in the sense that he's not even conceding that he's really talking about the non-location of the photon going towards the slit, and that's not a non-location.
That's the picture that comes forward. Now, how would you test this idea to see if it's actually describing reality, how the world works? Well, the first thing is you need some kind of mathematical equation that allows you to understand.
Yeah, right. Yeah, right. Like the math allows you to understand. Yeah, sorry. You know, it's not going to explain the math. But look, the math has simple variables in it, right? I mean, it has the constant, which is the speed of the material. It obviously has the frequency of the light, the period of the impacts. It has to do the thickness of the slits, which decide the probability of coming close to the slit material, right? The number of slits. I mean, it has the obvious variables are placed into the equation. So there's nothing mysterious about the math. And there's just a consistent ratio. The fact that field lines are consistent with mathematical relationships to the strength of a magnet, for example, is just a fact. So the fact that the field lines are going to be a consistency, there's going to be a consistency in the field lines around any material object, it's just a fact.
How this wave evolves, how it changes over time. And that equation came to us from Erwin Schrödinger. Whether you understand the mathematical symbols or not, it doesn't matter, but it's...
Right, and it's like none of these are... I get mass, okay, we got that. This is the distance between the slits and the background, I think. I mean, the wall. I don't know why an A would be in here. This acceleration would be kind of irrelevant. Velocity would sort of be irrelevant. But whatever. But who knows what this funky thing is here and this funky thing here. And who the hell knows? Looks like some sort of religious symbol. But anyway, who cares? Enough. I'll move on. Next... I mean, it's just, you know, anyway, so this isn't just, in my opinion, this is not very good science, right? It's just horrible science, actually. Disgracefully bad explanation of the reality. You didn't accurately describe the reality. You really can get that, right? Yeah, you get that. So anyway. Just looking at my history here, for some reason that, you know, the other page isn't on here for some reason. But anyway, till next time and such.